So today, as I was stating, we are looking at the law of conservation of matter. We've kind of seen a couple of other laws of conservation. We had the conservation of energy or heat. Energy is conserved, heat's conserved. It's just transferred, transformed. Same idea with matter. Law of conservation of matter can also be referred to as the law of conservation of mass. It basically says that however many things I start with, how much stuff I start a reaction with, I got to have those same number of atoms, the same amount of mass at the end of the reaction. We cannot create or destroy matter. It's basically what the law of conservation of mass says. It is only changed into a new form. So we make new bonds and we break old bonds, but it's still the same amount of stuff and the same number of atoms for each of the substances. So we're specifically looking at today balancing chemical reactions. I'm actually going to show y'all two ways to do this. Some of you will find one way more easier than the others. You kind of pick which method makes the most sense to you. So a little bit of a refresh about just chemical reactions in general. The left side of the equation is called your reactants. The reactants are always changed or turned into the products. Now, this particular reaction happens to be a double replacement reaction because I have two completely different things at the beginning and the end. But the reactants are always on the left, the products are always right. And this arrow has several different words that you might see in terms of a statement. So we could say that reactants produce products, reactants form products, reactants yields product. Any of those things would be valid. And we don't always have to have two things making two new things. We will see at some point in this unit how I could have one compound break apart into two little elements. Or we could have two elements come together to form one compound. So, I believe physical science only does 5 reactions, chemistry does 6. But there are several different types of reactions. On all of them, the arrow is basically we're switching from what we start with to what we end with. For example, if you happen to have these ingredients at home, you can try this after 4th period today. Take a little bit of baking soda, add a little bit of either vinegar or lemon juice. I'm trying to think. Yeah, maybe orange juice might work, may not. But definitely lemon juice or vinegar. If you add that to baking soda, you're going to be making carbon dioxide gas. That's one of the products. So you'll actually see it bubble up and foam up, releasing the carbon dioxide gas. You're also making another product, but it kind of stays behind. You don't really see it. And if you're using orange juice, you know, you might turn your baking soda orange, but vinegar and lemon juice, it just kind of stays its normal color. But we had two things coming together to form two new things. So a reaction is where one or more substances are converted into different substances. The law of conservation of mass says that in a chemical reaction, matter is not created or destroyed. So think of matter or mass as words that are interchangeable for our purposes when we're talking about the law of conservation of mass. So for example, let's say I have hydrogen. Hydrogen happens to be a diatomic element, which means it floats around in the air as H2. So inside my little blue box is one hydrogen molecule. Well, hydrogen will react with oxygen, who also happens to be a diatomic element, to produce water. It's very interesting to note that hydrogen is highly flammable and oxygen by itself is highly flammable. But when we put those two together and we form a new compound, we get water, which is used to put out fire. So it puts out the highly flammable things. Gotta love it. Now notice that we have to ensure that the same number of atoms are shown on both the left and the right side of the equation. So we can easily see that with my purple O's, we've got 2 O's on the left and 2 O's on the right. That one's kind of easy peasy. But with the hydrogen, in order to show that law of conservation of mass, it requires two H's, two hydrogen molecules, so two H2s, to react with one of the O2. And when it reacts to one of the O2, it's going to form two waters. This is what we mean by the law of conservation of mass. I can't just have one H2 and one O2 coming to make two waters. It's not possible. I don't have enough H's to make two waters. I can't just create H's out of nowhere. They have to come from somewhere else. That's what we mean by when we say matter is not created or destroyed. I can't just use the two H's and one of the O's to make one water because I can't destroy the other little O in the O2 molecule. So notice we can easily see that on the left side of the arrow, we have a total of 4 hydrogens and 2 oxygens. And on the right side of the arrow, we have the same thing. So these numbers that I put in front of the chemical formulas are called coefficients. And a coefficient will always multiply everything, all of the subscripts in the compound immediately behind it. So it's kind of like saying 2 times 2, that's how I got that 4. Same way over on my product side. This 2 multiplied by that 2, that's how I got the 4 H's. If there's not a number beside an element, it is assumed or understood to be a 1. So in water, H2O, we only have 1 O. And that coefficient in front not only multiplies the H, but it also multiplies the O to give me the 2 O's. So when we are trying to show that mass is conserved, we have to make certain that the number of atoms on the left side of the equation matches the number of atoms on the right side of the equation. This is called balancing reactions. So in all chemical reactions, the mass must be conserved. That means the mass of the reactants must equal the mass of the product. So in theory, if I started out with 5 grams of A and 10 grams of B, I better have a total of 15 grams of product. Because mass is conserved. Not only is the mass conserved, but the actual number of atoms are conserved. Now, the cool thing is I can actually use the fact that mass is conserved to determine an amount for a reactant or a product. So let's say I know that I have 5 grams of C, but I don't know how much D I use to make 25 grams of CD. So if I know that final product is 25 grams, I just need to figure out, hey, what's the number I need to add to 5 to get 25? So 25 minus 5 tells me that, oh, I need 20 grams of D in order to get the 25 grams of CD. So that's in terms of mass. So the total mass of the reactants has to equal the total mass of the products. So using this example, if I have aluminum and oxygen coming together to form aluminum oxide, what, type or talk in the chat, would be the mass of the product that we produce? If I had 14 grams of aluminum and 23 grams of oxygen, what would be my mass for aluminum oxide? Yep, Autumn and Cadence. So what did y'all do to get that number? Yep, you add. So you either end up having to add or subtract. It kind of just depends on what the missing piece is. I would not necessarily expect my physical science students to know that, hey, this is O2. That's something I would expect my chem kids to know. But you should be able to go from aluminum oxide, the name, to aluminum oxide, the formula. Not that we're likely to ask you to do that with balancing, but you should have the skills in your toolbox to go from the names to the formulas. But yes, ladies, y'all were correct. It was 37 grams. So this time I've got water and it is decomposing into hydrogen and oxygen. If I had 25 grams of water, what has to be my mass for my oxygen? Nope, whole bunches. So Jair, Cadence, Autumn, what'd y'all do that time? So I know for me, it's usually easier to see if I have it in that equation form. We know that the stuff on both sides of the arrows have to be the same. So that breaks down is the arrow, but we can see that we've got 25 grams and it tells me that 19 of it is hydrogen, which means, yes, y'all are correct. We had to subtract those numbers to get the mass of the oxygen, which was 6. So usually students find this much easier than they find balancing equations. It's just a matter of figuring out where your arrow is and seeing, hey, do I need to add or subtract to determine that missing blank? So this happens to be the same reaction as above. We don't know our water, but we do know, oops, almost wrote it in the wrong plot, that we had 82 grams of oxygen and 21 grams of hydrogen. So if I ended up with 21 grams of hydrogen and 82 grams of oxygen, how much water did I have to start with? Jair already anticipated my question. Thank you, sir. So that's kind of easy. And you will have some practice, some questions that are that straightforward. But most of what you're going to see is we're actually going to be balancing the atoms. We're not going to be looking at masses and masses. So we're going to be looking at making certain that the number of atoms of everything match to the left and the right of the arrow. So remember, I said that those big numbers that we placed in front earlier were coefficients. I did not state what the little numbers were because we've seen them before. But remember, these little numbers are subscripts. And if there's not a number, if you really want to, you can put a 1 there. Chemists are lazy and we tend not to write 1s, which is why there's not a 1 there. But I do know that some physical science students need those 1s there to remind them that, hey, there is one atom or one molecule of that substance. So describing the coefficients. The coefficient could be for an individual atom or an individual element. So I could be referring to just aluminum. or in this case, magnesium. So 2 Mg means I've got 2 atoms of magnesium. It can refer to a molecule. Molecules are specifically used with covalent compounds. So I've got 3 molecules of CO2, 3 molecules of carbon dioxide, or it can be referred to as, I say formula unit. Physical science, for some reasons, likes to say unit, but formula unit is used with ionic compounds. But basically, that coefficient is saying, hey, this is how many of these things we have. And if I have 4 units of magnesium oxide, that means I have 4 Mgs and 4 Os. If I had 3 molecules of CO2, that means I have 3 times 1, so 3 carbons, 3 times 2, 6 oxygens. Coefficients multiply everything in the compound that it is in front of. You are not allowed to shove coefficients between letters. You can only put them in front of compounds. That's the only place they can go. If you're trying to shove things in between letters, you are actually changing the substance, and that is not allowed. We're not going to see this very often for physical science, but sometimes chemists like to give you extra information in the equation. So you might see additional symbols. That is supposed to be an AQ, but it doesn't like it and doesn't quite look like a Q, but I promise it is an AQ. Solid, liquid, gas makes sense. You know, if I had aluminum, it would be solid. If I had water, it's typically a liquid. If I had oxygen, it's typically a gas. Those things, that makes sense. AQ, it just means something that's dissolved in water. So that would be something like a sodium chloride solution. That's saying that, hey, I put table salt in water. Not that it's needed for what we are going to be doing for physical science. Generally, you can just kind of ignore these phase abbreviations. You just might see them. You also, and I don't think you're going to actually see them any of this course, but if you happen to see a triangle over the arrow, it just means that there was heat involved. So some reactions will not progress unless we add extra energy to them. Can't talk. But we've already seen where the arrow can also mean reacts with, what was the other one earlier? That was not what I wanted to do. Oh, breaks down. That was the other one. So several different words could be represented by the arrow. The plus sign usually just is represented by the words plus or and. Very rarely do you see anything else that would be used to represent the plus sign. So think of an unbalanced equation kind of like a seesaw or a scale. The goal is to get everything to be the same on both sides. So right now I can see in this equation, I've got 1 magnesium on the left and 2 O's on the left. And then on the right, I've got 1 magnesium and 1 O. So one way you can think about balancing is by adding more of a compound that you don't have enough of. Like, for example, I can see that my O's on both sides don't match. I don't want to circle that there. But right now, my O's don't match. I need to figure out which side needs more O's. Well, that side that needs more O's happens to be the right side. So to get more O's, I'm just going to write another MgO. I'm putting it here a second time. That would be the same thing as just putting it on the scale as a second compound. So my MgO. When I add that MgO, I have now changed my counts. I can see that on the right side, I now have 2 Mgs and 2 Os. So every time you add either a coefficient or you add more of a substance, you do need to make certain to recount and see exactly what you have. So just, oh, nope. So now my O's are good. I have the same number of O's on both sides, but my Mg's don't match. Well, good news is Mg was all by itself. So I could just add more Mg's to the left side. Since Mg is not attached to the O, we can literally just write Mg, and now we have an extra Mg on the right side. So total, I now have 4 atoms on both sides. I have 2 Mg's and 2 O's. That means this thing is balanced. So if I wanted to write this using coefficients, I basically just state, hey, how many times did this thing appear above my count? So I can see that I've got Mg twice, so 2 Mg's. I only got O2 once, so I've only got 1 O2, extra large arrow. I can see that I've got 2 MgOs. That is one way to go from an unbalanced to a balanced equation. You can think of it like you are adding more of the compound that has the element that you need more of. Now, as I said, I'm going to show y'all 2 ways for balancing. So most students prefer this method that I'm about to explain right here to the previous one. Either way works. Pick the one that makes the most sense to your brain and kind of stick with it. So when you're going to balance an equation, you have to first have the unbalanced equation. For physical science, we tend to give that to you. We give you what I call the skeleton equation. It's the elements and their subscripts, but no coefficients. It doesn't tell us how mass is conserved. Once you have your skeleton equation written, you then list and count the atoms for each element on each side. Then, once you've done that count, you're going to add coefficients to make the numbers equal. Remember, the coefficient times the subscript will give you your number of atoms. You know, one of these days I will remember to actually add this to the thing, but many students like these extra little 2 reminders. So 2A, once you've done your count and you've actually listed and done that initial count, pick an element. Pick an element that's not balanced. So if it's balanced, you don't got to worry about it. General rule of thumb is to not start with your H's and O's. Leave H and O until the end. We don't see this too terribly much in physical science, but you do see it a lot in chemistry where the H's and O's tend to work themselves out. If you've got a choice, start with something else. Now, frequently, you're not going to have a choice. So you're going to have to start with an H or an O, and that's fine. So once you've picked that element, you're going to ask yourself, which side of the equation needs more? Then you can add your coefficient. You got to figure out for your coefficient, hey, what is my least common multiple? Now, frequently, you're not going to have to do this reduced step, but you do always want to check your coefficients to make certain they're not all even or, all a multiple of 3 or something. Because if they are, that means you've overbalanced and you don't have the true correctly balanced equation. Because the correctly balanced equation shows the lowest ratio of atoms needed to show the law of conservation of mass. So once you're done, you double check, make certain everything is correct, and you are good to go. So this part here where we are listing and we are adding coefficients, I guess I need to add a 3b recount. That part is what I call your element inventory. Yep, that's not going to show up very well. Purple. We must see your element inventory as you are balancing reactions at a minimum at the beginning and the end, but preferably every step of the way. You're going to show me how the coefficient changes your numbers. So let's look at an example. Al plus O2 yields Al2O3. So that's step 1. We have the unbalanced equation. Step 2, count and list the elements on each side. I usually just do it under the arrow, but I know our practice is set up so that we're having it on both sides. Honestly, it doesn't matter. So list the elements, make certain you list them in order. So I'm going to look on the left side of the arrow, and I'm going to see that, oh, I've got only 1 aluminum, and I've got 2 oxygens. And on the right side of the arrow, I've got 2 aluminums and 3 oxygens. So 2A, pick an element who is unbalanced. Well, nobody's balanced, so it doesn't matter who I pick. I can pick aluminum or oxygen. General rule of thumb says to leave O until the end. So I'm actually going to do that. You don't have to, but I actually am not going to start with my O. I'm going to start with my Al. Well, for my Al to figure out where I need to put the coefficient, I ask myself, hey, which side of the equation needs more Als? Well, that's the left. The left side of the equation needs more Als. So type or talk in the chat. What should we multiply it by to get this number of atoms to be the same? What should we multiply our 1 aluminum by to get them to be the same? Cheyenne and Dewan, I updated y'all. I thought I hit save at 11 after, but I just hit save again just in case it did not save the first time. Thank you, Jair and Cadence. So what they just did is they figured out the least common multiple. Least common multiple between 1 and 2 is 2. So what times 1 will give me 2? Oh, well, that's a 2. So I'm going to put a 2 in front, and that tells me that, oh, I've got 2 atoms of aluminum. Notice this coefficient only affects the compound it's in front of. So we fixed aluminum. Yay. Now we're going to go and try and fix oxygen. Well, this is a little bit harder because my numbers are 2 and 3. So in this case, what is my least common multiple between 2 and 3? And for those of you who don't remember your math terms, least common multiple is the smallest number that both of those can multiply and go into evenly. It's like, what can I multiply 2 by? What can I multiply 3 by? Get a number that's bigger that they both could go into evenly. That's what least common multiple means. And I'll give you a hint. Yep. 75% of the time, 80% of the time, you end up multiplying the 2 numbers. My least common multiple is a 6. No, you don't need to write that little green thing down. I'm just putting it there so that we can actually see that, oh, that's where that number came from. But my least common multiple is a 6. So I'm going to need to do something on both sides to get a 6. Just for giggles, I'm going to start on the product side. So what times 3 will give me a 6? What times your subscript will equal your least common multiple? Yep. So I put that 2 in front of the thing that contains the O. I can't shove it in the middle. I can only put it in front of it. That 2 changes both the O and the A out. And yes, we just broke the aluminum. But that's okay. I knew it was going to happen. That's why I did it in this order so that we can see that, hey, sometimes we got to make more than one change. So we've got the least common multiple of 6 on the right. Well, now I'm going to do the left. What times 2 will give me 6? Thank you, Cadence, right here. 3 times 2. 3 times 2 gives me 6. So we have fixed the O's. Yay, they balance. But my aluminums don't. And that's okay. Sometimes in the process of fixing one element, you break another one. So what I'm going to do to go and try and fix this is I'm going to pretend that that 2 isn't there. We're going to erase that 2 that was up top. And we're going to go back to the beginning and we're going to ask ourselves, okay, well, what's my least common multiple? Well, now it's a 4. I've got a 1 and I got a 4. What should my coefficient be in order for my number of aluminums to balance on both sides? And yes, y'all are correct. So 4 times, remember that invisible 1 gives me my least common multiple of 4. So now we are good. Step 4, do I need to reduce? Well, I've got an even and odd numbers. No, there's no reducing here, but we do want to double check. The way you double check is just literally rechecking your inventory. 4 times 1 gives me 4. Yep, that's right. 3 times 2 gives me 6. That's right. 2 times 2 gives me 4. Yep. 2 times 3 gives me 6. No, you don't need to draw all those little arrows. I was just drawing it to kind of show you where those numbers are coming from. Now, for those of you who are like Miss Rains, I don't like multiplication. I know me and multiplication don't get along. That's fine. You can do the other method and still get to the same place. So I'm going to pick on the same equation for just a moment. This way may take a little longer at first, but the more you do it, the faster you get. Instead of multiplying, you just have to think, hey, where do I need to add more to? You still have to do your inventory. So my initial inventory, 1, 2, 2, 3. So I pick something that doesn't match. We'll pick the aluminum. I'm going to literally rewrite aluminum above my inventory. And I now can literally visually see that, oh, I've got 2 of them. Yay, it matches. So I'm going to fix my O's. Well, I need more O's on the left. So I'm going to add an O2. That O2 on the left gives me now 4 O's. Okay. Well, now I don't have enough O's on the right. So I'm going to add one more of the thing that contains the O. Ooh, not that color. Al2O3. I have to write the whole thing on the right in order to get more O's on the right. I now can visually see that, oh, I've got 3 plus 3 gives me 6. And I can visually see my aluminums. 2 plus 2 gives me 4. My totals don't quite match yet. So I come back over to the left. I now need more aluminums on the left. I add 1. Okay, I see I got 3. I need 1 more. Ooh, now I've got, now I've got my 4. So to go from this hot mess to get your coefficients, you just count the number of times that that thing is written, including the first one. Like I count that original purple. I got 4 aluminums. I got 2 O2s. And I got 2 Al2O3s. Balancing by addition or balancing by multiplication will get you to the same place. Pick which makes more sense to you. You hopefully by now have a little bit of an idea of how your brain works with math. And if you know the whole least common multiple thing may not work for you, then give the other method a try. So pick one of the methods you want to try. I'm going to pause for 2 minutes. I want you to at least do your initial count. At least do your initial element inventory. Once you've done that inventory, try and figure out where and what coefficients you need to add. You've got 2 minutes. Well, now slightly less than 2 minutes. That little dotted line's not necessary, but it might be useful for some students as a visual of this is the left, this is the right. Remember, my left are my reactants, my right are my products. So nothing on the left has a subscript. That means we have one of everything. If you are listing your elements twice, like I have been doing today, make certain you put them in the same order. It makes your life so much easier to be comparing elements lining up in the same row. So on the right side, I've got 1 zinc, 2 H's, and 2 Cl's. So notice they don't always go in the order that they appear in the equation. So which element should we try and balance first? So anybody, why did Cadence not select zinc? Why did she not select Zn? I mean, it's listed first, so you would think you would balance it first. Any idea why Cadence did not select Zn? Thank you, Autumn. You were correct. They already matched. They had one of each, so I didn't need to mess with it. And I suspect the reason she chose Cl versus H is she remembered my general rule of saving H's and O's till the end. I usually tell my chem kids that they are the hose of the periodic table. My H's and O's like to bond with everything. So we mess with them at the very end. So we're going to fix chlorine first. Well, I found my element. Now I got to ask myself, which side needs more? Well, that's the left side. So I could do the whole least common multiple thing. Least common multiple between 1 and 2 and 2 is 2. Or I could just come up here and be like, oh, I know I need more HCl's because that's the thing that has the Cl in it. I have to add the entire compound. Now this equation is balanced. It takes 1 zinc reacting with 2 HCl's to produce 1 zinc chloride and 1 hydrogen. And yes, sometimes balancing is that easy. Just one thing that needs to be changed. So had I done the least common multiple, I would have figured out that, oh, I needed my coefficient to be a 2. You get to the same place. It's just visually adding more, you're more having to think of counting and where you need more compounds, less about multiplication. All right, so a little bit harder example. Again, make certain you're listing the elements in the same order on both sides. So the only thing that doesn't match is my chlorine. Which side needs more? Technically the left. I could do the least common multiple and realize that I needed to get up to 6. Or I could just write another copper chloride and see that that gives me 2 and 4. Which means now the product side, don't want to do that color. That color does not show up very well. I need more chlorines on the product side. So now I can see that visually I have 2 aluminums and 6 chlorines. Chlorines still don't match, but now I need more on the left. Oops, bad misreadings. Pretend that U's a little bit smaller. Oh, now I've got 3 and 6. So we fixed the chlorines. Least common multiple would have told me that, hey, I needed a coefficient of a 3 on the left and a 2 on the right to get my 6 chlorines, because that is the least common multiple between 2 and 3. So we still got to fix the Al and the copper. I don't care which one you fix. Pick one, doesn't matter. I'm going to go on the product side just because I feel like being non-typical. So I need more coppers over here. I need a total of 3. So I'm going to write copper until I get a total of 3. Or least common multiple is 3. I need is a 3 as my coefficient. 3 times 1 gives me 3. My aluminums don't match. That's all right. Going to come over here and I'm going to realize that, oh, I just need 1 more aluminum. Or I need my coefficient to be 2 in order to have the total of the 2 aluminums. So remember, if you're doing the method where you're adding, your coefficients ends up being the total number of times that that thing is represented on your paper above the element inventory. Yeah, okay. So one last one. We do have some combustion on our practice. You're not going to see a lot of these, but you don't know how to handle it when you have 2 elements, Miss Rains, when you have the same element on the same side of the equation more than once. Well, the equation gives you a hint. If you happen to have a situation where you have the same element on the same side more than one time, you have to add them together. I generally prefer literally showing that addition as a reminder to myself that it's in 2 places. This is one of those situations where, yes, you definitely don't want to start with your H or your O. Bad, Miss Rains, for not counting the C's and the H's. 1 and 2. You don't want to start with your H or your O. You want to start with something else. Combustion is a perfect example of not starting with H's and O's. So, gonna do the least common multiple method on this one. First element I'm going to pick on is carbon. Which side needs more? Well, that's the right. My least common multiple between 1 and 2 is 2. So I've got to put a 2 because 2 times 1 gives me 2. But that 2 also changes the number of O's right there. That means we now have 4 O's from the CO2 and only 1 O from the water. This is why I show it being added separately, so that I don't think that, hey, I have 3 O's in CO2. No, I only have 2 there. These numbers only multiply the things up top. They do not multiply the things in inventory. Yeah, this is an ugly one. So I'm going to fix my H next. Since O2 is by itself, H makes the most sense. I got 2 and I got 6. Least common multiple is 6. So what times 2 will give me 6? 3 times 2 will give me a 6. So I got 6 H's and 3 O's. I'm only changing that O right there. All right, so now we're at a spot. I got a 2 and a 7. What is my least common multiple? Between 2 and 7, what should be my least common multiple? So I need a number that is bigger or equal to the largest number, so 7. But 2 cannot evenly go into 7. So my least common multiple cannot be 7. Which means I'm going to try the next thing, and I'm going to take 2 times 7 and get 14. My least common multiple in this particular situation is a 14. So to get the 14 O's on the left, it's not too hard. We just multiply by 7. But we need to get a total of 14 on the right. Well, in order to turn 7 into 14, what would I need to multiply it by? Yay. Now, because this is in 2 different places, these numbers are coming from 2 different compounds. We do need to multiply that 7 by a 2, but to accomplish that, we're going to multiply those coefficients by a 2. So I'm not going to actually erase it. I'm just going to cross it out. So I know I need to double it. I know I need 14. And the easiest way to get 14 would be to double each of the numbers that we're getting. So I need 4 CO2s and 6 waters. That will give me my 14. We see this semi-frequently with combustion, where you get to where the O doesn't match. And the trick I tell my chem kids is to try doubling your coefficients. If you double your coefficients that you currently have, you usually get to the answer. That was not the color I wanted. Now, because we changed the coefficients on the right, we still need to recount those things. So 4 times 1 gives me 4. 4 times 2, that's the 8. 6 times 2 gives me 12. 6 times 1, that gives me the 6. We know this is correct. It matches. But in the process of trying to fix the O, we broke the C and the H. So what should my coefficient be in front of C2H6 in order to have the right numbers of C's and H's? Again, you can think least common multiple. It's either going to be equal to or above the largest number. So if I'm looking at my C's, I've got a 2 and a 4. Well, it could be equal to 4 because 2 can go evenly into 4. So that means I've got to multiply by 2. Get the same answer if I looked at the H. I had 6 and 2. I'm sorry, 6 and 12. My least common multiple can be 12 because 6 can go into it evenly. So now I've got 4 and 12. So double check your counts. Make certain they're correct. I did not mean to erase everything. I apologize. Hit the wrong button. But that's fine. It gave us a nice print, clean surface to do my recount. I got 2. Bad, Miss Rains. I don't have 2. I've got 4. I got 12. I have 14. I got 4. I got 8. I got 12. And I got 6. That's about as hard as it gets for physical science. For your practice today, the first couple of questions are just kind of constructive response, reviewing the idea of conservation of mass, looking at mass. The next couple equations, I give you some equations and I give you some with coefficients. And you've got to tell me the inventory and if they are balanced or not, and why or why not. The last couple, I'm giving you the skeleton equation and only the skeleton equation. I expect you to balance it, but I also expect to see your element inventory. At a minimum, the initial and final counts. Ideally, I would want to see all of the counts, but I know that some of you, for some of these problems, you're going to be able to do them in your head. And I'm trying to be, respectful of that and say that, okay, well, at least give me the initial and the final count. 2 plus 1 gives me 3. So like my initial counts were in green, final counts were in blue. And y'all saw earlier as I was changing them as I went, sometimes we change numbers multiple times. Like this one is a good example of showing the changes in the inventory as you go. You pick which method you do. You do not have to type. For the love of God, if you do not want to type, you do not have to type. Just do it on a piece of paper, show your element inventory, and make certain you give me that balanced chemical equation. I need the balanced with the coefficients at the very end. So even if you're doing the addition method, I need you to rewrite it and tell me how many you actually have in your completed equation. We have got about 20 minutes to practice. Sweet. So as you're doing the practice, if you've got questions, you can send them to me either through GoGuardian, or you are more than welcome and encouraged to ask them in the meet. Your question might benefit somebody else.